Hey everybody, and welcome back to Physics 101. Today we're talking about forces, one of the most important topics in all of physics. Today we're going to be mostly focusing on Newton's three laws of motion, and they are quite famous. I'm sure everyone, even if you haven't studied physics, knows of them, or some of them maybe even. So why don't we get into it with the first one? Every object persists in its state of rest or uniform motion in a straight line unless it is compelled to change state by forces impressed on it. So this is a kind of fancy way of just saying an object will stay at rest, it will not move, or it will stay in uniform motion, meaning it will not accelerate, it will just stay in a constant speed unless a force acts on it. This is a very important concept to understand. Mostly what it means is that if, let's say, I'm going to draw this out just to make things even clearer. Let's say a ball is on, oh, that was a terrible ball. Let's say a ball is rolling, it's going this way, and it's moving at a constant speed on ice. Ice um, is has very little friction compared to other materials, but it does have friction. But let's just say for these purposes that we are on this ball is on frictionless ice, which is impossible. But just for the sake of the question, the ball is on frictionless ice, and someone pushes it, and it starts moving at a constant speed to the right. According to Newton's laws of motion, the ball will stay in motion. It will continue forever until a force stops it or speeds it up. It will continue to go at its speed until a force acts on it. Similarly, if the ball wasn't moving, it was just sat there on a surface, let's just say it's on the ground, it's just sitting on the ground, it will stay on the ground. It will not move until a force acts on it, which makes sense. I mean, objects are not going to move on their own. They're going to move when someone pushes them or anything exerts a force on it. We have a little definition here. Isaac Newton also came up with this idea of inertia, where, here, let's just read it. Inertia is the resistance of any physical object to any change in its velocity. So what this is kind of saying is that objects, they don't want to change their velocity unless they require a force to change their velocity. They're not going to do it on their own. So you think of a big object. A big object means it has a lot of inertia. Something with high mass means it has high inertia. Something that's really big doesn't like to move. It prefers just to sit there. So you're going to need a pretty big force in order to move that object, which makes sense. You need to apply greater forces to move bigger objects. Okay, so that's Newton's first law of motion. And I just like to add on that if something is moving in at a constant speed, that doesn't mean that there are no forces acting on it. This is really important. Just because an object is moving at constant speed or just at zero, that doesn't mean there are no forces on it. What this means is it could mean that there are no forces on it, but it could also mean that there are opposite forces, meaning coming in from different directions that are equal in magnitude and are therefore canceling each other out. What I mean by this is if, let's say, okay, this ball is rolling and the friction force is obviously going to try and slow it down. So the friction force would act in that direction. Let's say something is manually pushing this ball at a force of, I don't know, just any random 20 newtons, and frictional force is 20 newtons as well. The ball is getting pushed, so it is going to be moving just at a constant speed. So essentially, just because an object is in constant, just because an object is in constant motion, that does not mean there are no forces on it. There could be forces on it. They're just canceling each other out, resulting in a resultant force of zero. Okay, right. So now on to Newton's second law, and this is his most famous law by far and most important one in physics. Force is equal to, okay, we're going to ignore the first sentence here because this has to do with momentum. We're going to get to that in a later topic, but let's just focus on this second sentence here. For a constant mass, force equals mass times acceleration. F equals ma. Now, I've even written it out here because it is the most important equation in all of physics. You're going to see this not just in forces, you're going to see this throughout all of physics, really. It's the foundation of all physics equations. It's the foundation of all of physics. So what it means is, I mean, it's pretty simple. Force equals mass times acceleration. So if you want to figure out, okay, what's the force, the downwards force of on a ball that is falling from the sky after I've dropped it from a building, right? So let's say I've dropped the ball out of my window, right? I'm 10 stories up. What's the downwards force? All right, well, force equals mass times the acceleration. So we need the mass of the ball. Let's say it's a heavy ball, it's 10 kilograms, and then we'll times it by the acceleration. Now, what's the acceleration? Well, the acceleration is going to be the acceleration due to the gravitational force on Earth, which is 9.8. 9.81, but we'll just say 9.8. Last video I was calling G, which is the constant of acceleration due to gravitational force. I was calling it the gravitational force, which is not technically correct. It's the acceleration due to the gravitational force. So the acceleration, this might as well be a G just for this case. The acceleration can be something else, but basically the force is 98 newtons. Force is measured in newtons. It is 98 newtons. That's the force of gravity on the ball in this case. It depends what your mass is, what the object's mass is. So pretty much, we're going to use this equation a lot for figuring out. Mostly we use it to figure out what the acceleration is of an object, and what it does tell you straight away is that in order to make something accelerate, you have to apply a force, a resultant force. There cannot be an acceleration without a force. What I mean by resultant force is, like I said with this ball, if you apply a 20 newtons of force to the left and 20 newtons of force to the right, that's not a resultant force. The ball is not going to change. It's not going to accelerate. It's going to stay the same. You need to apply a resultant force. So if this was 21, you've got a resultant force of 1 newtons. It's going to accelerate. Okay, so now we have the third law. This is a bit of a lesser on the scale of importance, but it's still an important law. For every action, there is an equal and opposite reaction. Right. So when you stand on the Earth, funnily enough, the Earth obviously is going to exert a force on you, and you are going to exert a force on the Earth. And both of these forces are the same in magnitude, but the opposite in direction. So let's say you're on the Earth, right? Let's say you jump. Let's say you jump up. When you come back down and you land on the Earth, you're going to apply a force, and the Earth is going to apply the exact same force in terms of numbers, but opposite in direction. And these are going to cancel each other out. If you fell through the Earth, obviously this force would be bigger, but this is why we don't fall through the Earth, because the reaction is, the action and reaction are the same in size or magnitude, but opposite in direction. We don't really use this law too much in other branches of physics. We just kind of use this to understand what forces are occurring on objects. Now, I've written some forces here. So we've got applied force, gravitational force. Applied force just means pushing something or applying a force. A gravitational force, we know what that is. Gravity is attractive and it's going to pull things towards it. The Earth pulls us towards it when we jump. That's why we don't just float off. Normal force. The normal force is kind of what we're talking about here. Normal force is the reaction force, right? So for every action, or for when you jumping up and down, when you land, that's the action force, you're applying a force on the earth, and the reaction force is going to be also known as, well, that's not really the normal force. The reaction force is going to be the earth back when you, let's say you're standing on the earth, you don't even need to jump, it's meant to be here, but I'm just going to draw it to the side. The action force, or the force of gravity, right, is down, and then up is going to be the normal force, right? So when you're just standing there, gravity is acting on you, and the normal force, or the reaction force, is you acting on gravity. So obviously these go in opposite directions, and this is why you don't fall through the earth, because they're equal and opposite. So they cancel each other out. There's no resistant force. If the gravity for some reason was acted bigger, although this is impossible, you would fall through the earth, but it's not. It's equal and opposite. Okay. Now I've written out here free body diagrams. So this is to label the forces acting on an object. So a very common one is an object, a block or whatever, on an inclined plane. So actually, I'm going to make some space here. I'm going to use this instead. Oh, actually, sorry guys, 1 second. Okay, I'm just going to draw this here. Ugh, I can never draw straight lines. Okay, so here's an inclined plane. And here is a block, right? Sitting, a brick, whatever, on the plane. So let's draw a free body diagram. What that means is draw the forces acting on the brick. And when you draw, I'll show you how to draw it exactly. So you always have to draw it from, the lines have to come from the center of the object, the center of mass. So like I said, we already know straight away there's a gravitational force. Now this is a straight down force. We'll label it F of G, gravitational force. And now the normal force. Now the normal force is not just straight up. It's not like that, okay? What it is that's actually perpendicular. Now I know that can be confusing. Even I don't really get it. But this is the direction of the normal force. And let's say every surface has a friction. There's always a frictional force, so we'll label this, I'm running out of room, but F of F. Right, frictional force. Should probably make this bigger. Okay, and yeah, we'll leave that as is for now. Alright, so that's a free body diagram. Now, one important aspect, and I haven't really taken the time to do here, is the length of the arrows represent the magnitude. Okay, so obviously what direction the arrow is the direction, but the magnitude is meant to be the length of the arrow is the magnitude. Now these two should be the same. The normal force and the gravitational force should be the same, because remember, the normal force is a reaction force, so they're going to be equal, definitely. Now the frictional force I've just left as this. Don't ask me why, but that's quite large for a frictional force. But it's just a demonstration. It's just an example of what a free body diagram looks like. Okay, so now we've gone over the 3 laws, and we've gone over how to make a free body diagram. So why don't we go over, I've listed 3 questions here. So let's go through these. A box is accelerated to the right across rough ground by horizontal force. Now I had to, because in Microsoft Paint they don't let you do subscripts, I had to write it like this, but you are meant to label forces like so. Do not do it like this. Make sure you label it F subscript A or F subscript F, whatever. It cannot be that though. Anyway, the force of friction is F of F. The weight of the box is F of G, and the normal reaction is F of N. which is the free body diagram for this situation. Okay, so let's draw this out. So a box is accelerated to the right across rough ground by a horizontal force. Okay, so this is the box, and it's on the ground. Yep. It's accelerated to the right. So straight away, we know that we are going to draw an arrow this way. And it's going to be a long arrow because it's accelerated. So the force going to the right is going to be greater than the force going to the left. So we F of A. Oh my goodness. F of A. Sorry, I know it's terrible, but that's F of A. Rough ground, yep, force friction is F of F. So there's clearly a frictional force, and it is not greater than this. Obviously, I've made this arrow bigger, so that's what should be done. So F of F, right? The weight of the box is F of G. I mean, we could have drawn this, we knew that anyway. And the normal reaction is F of N. Let's go straight up. And these two should be equal in length. Remember, our reaction force has to be equal in length, opposite in direction, which they are. Which is the free body diagram for this situation. All right, so which one most looks like this? I mean, this is terrible, but we know these two are going to be the same, and F of A is going to be greater than F of F. So first one, there's F of N is just missing. The normal force is literally missing. Here, the gravitational force is missing. So it's between C and D. Now, let's see, we know F of N and F of G are the same. They're both in this case. So now we're left with two, F of F as being greater than F of A and F of F being smaller than F of A. Well, we know if the box is accelerating, so F of A is going to be bigger. So the answer is D, and that is the correct answer. Okay. Now, a parachutist of total mass 70 kilograms is falling vertically through the air at a constant speed of 8 meters per second. What is the total upward force acting on the parachute? Okay, what is the total upward force acting on the parachutist? Not what is the total force. Okay, that's going to be key. Because straight away, when I see constant speed, I'm going to think no force, right? Because remember what we said, a force, if there is no force, an object's going to be motionless or it's going to be moving at constant speed. But it's asking what is the total upward force. So I see 0 newtons, but we want the total upward force. Okay, so the parachutist's mass is 70 kilograms and it's falling constant speed at 8 meters per second. What is the total upward force? Okay, so upward force. So let's go to our equation. F equals ma. Right? Okay. So what is the total upward force? Now he's moving at constant speed, right? And we know what the downward force is going to be. That's going to be the downward force because he's jumping out of the sky, and well, we know what the gravitational force is. So he's 70 times. We're just going to call it 10 because these seem very rounded numbers. Equals 700. So the downward force is going to be 700. Now he's moving at constant speed. Doesn't even matter what his speed is. It's constant. So if it's constant, then his upward speed is going to be exactly the same, right? Because there's no resultant force. So his upward has to be 700. And would you look at that? 700 is an answer, and that is the correct answer. I think the adding in the 8 meters per second is just kind of throw you off. It's telling you that he's moving at constant speed, which should tell you that the downward force and upward force are exactly the same. Okay, last question. Which statement applies to an object in translational equilibrium? Okay, don't look quickly. I forgot to mention translational equilibrium means an object is moving is either in rest or is moving with constant speed. And so what that means is equilibrium, as you see the word equilibrium, that means there are the forces acting on the object are equal to 0. So usually this means that object is moving at constant speed, and the forces acting on it are zero. If the force of friction here and the force of acceleration were the same, in this case, this object would be moving in translational equilibrium because the resultant force is zero, and if the object's motionless, it's in translational equilibrium. If the object is moving at constant speed, it's at translational equilibrium. So which statement applies to an object in translational equilibrium? The option must be stationary. Well, we know that's wrong because an object can be in translational equilibrium with, just like here, the forces canceling each other out. The object must be moving with constant acceleration. No, that is completely the opposite of what translational equilibrium is. The resultant force acting on the object must be zero. So clearly here, I think we're onto something. Just like here, if the object is moving or not doesn't matter. All the forces are canceling each other out. C is our answer. There must be no external forces acting on the object. Don't be fooled. Translational equilibrium does not mean there are no forces acting on the object. It means all the forces add up to zero. That is the correct answer, C. Okay, so that was forces. We're going to come across forces a lot more in the future. I just thought we'd go over 3 laws and also free body diagrams because they come up quite a lot in exam questions. But I think we covered a lot of stuff. If you guys have any questions like this and you want to know how to do it or why an answer is what it is, or you just have any questions, maybe I left something out that you're curious about, just email me. I've got the email in the description and I'll respond to you as soon as possible. Okay, thanks guys, thanks for watching. Like, subscribe, and I'll catch you guys in the next video. See ya.